So at this point we have all of the major tools we need to prove the inverse function theorem, but there are still some minor tools that we're missing. And these are sort of things that I could insert their proofs inside the proof of the inverse function theorem, but it'll just be cleaner if we prove them separately. And they're useful facts on their own. For example, a composition of C1 maps is C1. For some reason, we don't have that to reference anywhere, so let's prove it. Of course, we know from the chain rule that a composition of differentiable maps is differentiable, but C1 is saying a little bit more than just differentiable. So first, let's set up the assumptions in a precise way. So let's talk about two C1 maps where they're composable. So assume that F is a C1 map on the set E, let's say into Rm, where E is a subset of Rn. And assume G is a C1 map on, let's call it D to Rk, where they're composable. So not only is D a subset of Rm, but also the image of E is contained in D. And I should mention these are open. Okay, so now we can talk about G composed with F, and the claim, so what we must prove, is that G composed with F is C1 from E to Rk. So again, we already know that G composed F is differentiable at any given point in E, just due to the chain rule. What remains is the question of, is the derivative continuous? So the derivative is going to be this mapping. So we must prove that the following mapping is continuous. The mapping from x to what the chain rule tells us is the derivative, is G prime fx composed with f prime x. So we must prove that this mapping is continuous on E. Okay, so let's prove that it's continuous at x. So let x be in E, and let epsilon be greater than 0. Let delta be, and then we have to decide here what delta is, and let's decide later. Then let y be in a ball of radius delta centered at x. Then we have to prove that, so let's see, what do we need? We need that the output of this mapping, which is a linear map, at x compared to the output at y, the distance is less than epsilon. So here, these double norm bars indicate that I'm doing the norm of a linear map. So we know that the f prime, and we know that f prime is continuous at x. That was one of our assumptions, that f is a C1 function. So we know f prime is continuous at x, and we also know that g prime composed with f, which is the function we see evaluated at x here and at y here, that's also continuous at x. Why? Because it's a composition of continuous functions. So f is continuous because it's differentiable, differentiable functions are continuous. And g prime is continuous because we assumed g is a C1 function. So we know these are both continuous everywhere where they're defined, but specifically we're interested in continuity at x. So how can we use this fact? Well, this looks like kind of a... it's similar to a product situation. If you remember when we were... when you're working with, like, trying to prove that the limit of a product of sequences or a product of functions converges to the product of the limits, it's really similar to that. The continuity of f prime and of g prime compose f individually tell you things about the norm of the difference f prime x minus f prime y, or g prime fx minus g prime fy. So to bring in those individual differences, I can add and subtract a term like this. So we have let me make more space for it. I don't need these words. Okay, this thing equals, and then let me add and subtract something. How about I subtract here g prime fx composed with f prime y, and then I add that back in. Let me make some space here. Composed with f prime y. Okay, and the norm bars there are off screen, but they're there, I promise. Now here you've got the same term here and here. So it's as though I'm composing g prime fx. It's as though I'm composing that linear map with the difference of linear maps f prime x minus f prime y. So let me use the triangle inequality and pull some stuff out at the same time. So here I've got g prime fx composed with f prime x minus g prime fx not sure what happened there, minus f prime y, close norm bar, plus norm bars, and then here we've got, it looks like, and this is not, this composition is not like multiplication, it's not commutative, right? So I have to keep the composition in the correct order. G prime fx minus g prime fy, and then all that composed with f prime y. All right. Now, the norm of a composition of linear maps actually is the composition of the norm. So if you forgot about that, let me show you. So right here, the norm of the composition of linear maps, so here these linear maps are being composed, this is in theorem 9.7, is bounded above by the product of the norms. I should have said, I think I misspoke and said equality. It's less than or equal to. So the norm of the composite is bounded above by the product of the norms. So here we get less than or equal to times the norm of f prime x minus f prime y plus the norm g prime fx minus g prime fy times the norm of f prime y. Okay, well, this is probably seeming like a familiar situation when you're working with limits of products. So this is just a constant, right? X is fixed. So no problem. This we can make very small by making y be close to x, thanks to the continuity of f prime. This we can make very small by making y close to x, thanks to the continuity of g prime composed with f. And this is a problem. This is not a constant. However, if we can bound this, then there's no problem. And it should be something we can bound, thanks, again, to the continuity of f prime. So let's think about what kind of delta we need up here, where we left a blank. So the delta here is actually going to use the fact that f prime and g prime composed with f are continuous. So this comment here about f prime and g prime composed with f being continuous at x, I should have made this comment before choosing delta, because I will use this fact. So let me rearrange things a bit. Let's move all of this stuff down here. And then make sure this comment shows up before we decide what delta should be. And now I have a good feeling as to what delta should be. It should make this quantity here be less than epsilon over 2 times 1 over this quantity. And it should make this quantity here smaller than epsilon over 2 times 1 over whatever bound I can get for this quantity. So let's talk about bounding this guy. Let's see. I guess the discussion about bounding this guy should come before all of this stuff here. So we're going to make delta the smaller of a bunch of deltas, right? Okay, so let me actually bring this down, and let's just admit that delta has to be the smaller of delta 1, which will be a delta that makes this small enough, delta 2, which is something that makes this small enough, and delta 3, which ensures this is bounded. Actually, that third one, we can just make it be 1. That should be enough. So let's just say delta is the minimum of delta 1, delta 2, and 1. And here we can decide what are delta 1 and delta 2. So choose delta 1 such that, and let me fill that in after. Choose delta 2 such that, and let me fill this in after. And let me come down here and make use of this 1 here, since delta is smaller than 1. Oh, actually I should fill these in right now. Well, okay, let me fill in one of them. So to make use of the 1 here, I need to fill in the delta that's going to ensure that f prime of y is always close to f prime of x. So let's make that be delta 1. So choose delta 1 such that whenever y is within delta 1 of x, f prime y is within is within this distance of f prime x. So here I'm dividing by this thing here. But it might be 0. In case it's 0, let me just make sure I'm not dividing by 0, like that. So actually now, I'm not sure that I actually need this one anymore. This line here ensures that f prime of y, that the norm of f prime of y cannot be too big. So let me put in something in the space here. After we fix y within delta of x, then y is also within delta 1 of x. So this inequality holds. So after we fix y within delta of x, we have, let's say, note that the norm of f prime y is going to be less than or equal to, and then, do this trick where you subtract and add f prime x, and then use the triangle inequality. The norm of f prime of x is something that's independent of y, so that's something we can use in our choice of delta 2. And this thing is bounded like so. It's bounded above by this quantity. So epsilon over 2 like that. Now, this is kind of annoying to keep repeating this, so how about we give this a name? So let me make some space here, and let's give that thing a name. Okay, there's some space, so let's just define. Let m equal this quantity here. Our nice upper bound for the f prime of y's running over y within delta of x. So let's just call that m. Then by the time we reach down here, we have that nice name, m. And notice m is definitely greater than 0. So now I can include m in my choice of delta 2. And I'm convinced now that I don't need this 1 over here. I just need delta to be the minimum of delta 1 and delta 2. So choose delta 2 such that whenever y is within delta 2 of x. So now I'm going to use the continuity of g prime composed with f at x. So the goal here is to control this term down here. G prime f y minus g prime fx, and then take the norm of that linear map. We want that to be less than, I don't know why I wrote less than or equal to here, less than here and less than here, epsilon over 2 times 1 over n. So just a quick sanity check. The problem down here with trying to make this thing small is this thing could be large and fight it. The largeness of this thing is no more than the largeness of m. And the larger m is, the smaller my sort of epsilon kind of on the right-hand side of this inequality is, which feels right to me. So that's a good sanity check. Okay, so now we should be able to proceed. Delta is the smaller of delta 1 and delta 2, so y is both within delta 1 of x and within delta 2 of x. And so now down here, this is less than this times, let's see, here, I've got, my face is covering it right now, this thing here, epsilon over 2 times that thing. And this is less than epsilon over 2 times 1 over m. And this thing is less than m. Or less than or equal to m. And that's all less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay, sorry that that was out of order. Sort of going back and filling in things as we went. Although sometimes it's nicer to see a proof in that done that way. I don't know. But there we go. A composition of C1 maps is C1. So we have proven this less than epsilon at the end here. We have proven that the mapping here, which is the x goes to the derivative of g compose f at x, we've proven that that's continuous.